current sea level rise is about 3 a year worldwide. According to the U.S. National Oceanic and Atmospheric Administration, this is a significantly larger rate than the sea level rise averaged over the last several thousand years, and the rate may be increasing. Sea level rises can considerably influence human populations in coastal and island regions and natural environments like marine ecosystems. Between 1870 and 2004, global average sea levels rose a total of 195 m, and 1.46 m per year. From 1950 to 2009, measurements show an average annual rise in sea level of 1.7 a plus or minus 0.3 m per year, with satellite data showing a rise of 3.3 a plus or minus 0.4 m per year from 1993 to 2009. The reason for recent increase is unclear, perhaps owing to decadal variation. It is unclear whether the increased rate reflects an increase in the underlying long-term trend. There are two main mechanisms that contribute to observed sea level rise: thermal expansion, ocean water expands as it warms, and the melting of major stores of land ice like ice sheets and glaciers. Sea level rise is one of several lines of evidence that support the view that the global climate has recently warmed. The global community of climate scientists confirms that it is very likely human-induced warming contributed to the sea level rise observed in the latter half of the 20th century. Sea level rise is expected to continue for centuries. In 2007, the Intergovernmental Panel on Climate Change projected that during the 21st century, sea level will rise another 18 to 59 cm, but these numbers do not include uncertainties in climate carbon cycle feedbacks, nor do they include the full effects of changes in ice sheet flow. More recent projections assessed by the U.S. National Research Council suggest possible sea level rise over the 21st century of between 56 and 200 cm. The Third National Climate Assessment, released May 6, 2014, projects a sea level rise of 1 to 4 feet by 2100. 30 to 120 centimeters. On the timescale of centuries to millennia, the melting of ice sheets could result in even higher sea level rise. Partial deglaciation of the Greenland ice sheet, and possibly the West Antarctic ice sheet, could contribute 4 to 6 am or more to sea level rise. Work by a team led by Veerabhadran Ramanathan of the Scripps Institution of Oceanography suggests that a quick way to stave off impending sea level rise is to cut emissions of short-lived climate warmers such as methane and soot. Overview of sea level change, local and eustatic sea level. Local mean sea level is defined as the height of the sea with respect to a land benchmark, averaged over a period of time long enough that fluctuations caused by waves and tides are smoothed out. One must adjust perceived changes in LMSL to account for vertical movements of the land, which can be of the same order as sea level changes. Some land movements occur because of isostatic adjustment of the mantle to the melting of ice sheets at the end of the last ice age. The weight of the ice sheet depresses the underlying land, and when the ice melts away the land slowly rebounds. Atmospheric pressure, ocean currents and local ocean temperature changes also can affect LMSL. Eustatic change results in an alteration to the global sea levels, such as changes in the volume of water in the world oceans or changes in the volume of an ocean basin. Short-term and periodic changes, many factors can produce short-term changes in sea level. Longer-term changes, various factors affect the volume or mass of the ocean, leading to long-term changes in eustatic sea level. The two primary influences are temperature, and the mass of water locked up on land and sea as fresh water in rivers, lakes, glaciers, polar ice caps, and sea ice. Over much longer geological time scales, changes in the shape of oceanic basins and inland Euro-sea distribution affect sea level. Observational and modeling studies of mass loss from glaciers and ice caps indicate a contribution to sea level rise of 0.2 a 0.4 a millimeter per year, averaged over the 20th century. Glaciers and ice caps, each year about 8 mm of precipitation falls on the ice sheets in Antarctica and Greenland, mostly as snow, which accumulates and over time forms glacial ice. Much of this precipitation began as water vapor evaporated from the ocean's surface. If no ice returned to the oceans, sea level would drop 8 m every year. to a first approximation, the same amount of water appeared to return to the ocean in icebergs and from ice melting at the edges. Scientists previously had estimated which is greater, ice going in or coming out, called the mass balance, important because a non-zero balance causes changes in global sea level. High-precision gravimetry from satellites and low-noise flight determined that Greenland was losing more than 200 billion tons of ice per year, in accord with loss estimates from ground measurement. The rate of ice loss was accelerating, having grown from 137 gigatons in 2002 to 2003. The total global ice mass lost from Greenland, Antarctica and Earth's glaciers and ice caps during 2003 to 2010 was about 4.3 trillion tons, adding about 12 to global sea level, enough ice to cover an area comparable to the United States 50 cm deep. Ice shelves float on the surface of the sea and, if they melt, to a first order they do not change sea level. Likewise, shrinkage expansion of the northern polar ice cap, which is composed of floating pack ice, does not significantly affect sea level. Because ice shelf water is fresh, however, melting would cause a very small increase in sea levels, so small that it is generally neglected. The melting of small glaciers and polar ice caps on the margins of Greenland and the Antarctic Peninsula melt, would increase sea level around 0.5 m. Melting of the Greenland ice sheet or the Antarctic ice sheet would produce 7.2 m and 61.1 m of sea level rise, respectively. The collapse of the grounded interior reservoir of the West Antarctic ice sheet would raise sea level by 5 to 6 m. The interior of the Greenland and Antarctic ice sheets, as of 2009, was sufficiently high that it would require millennia before those sheets would be lost by direct melt alone. Those ice sheets would be substantially reduced in mass through acceleration in flow and enhanced iceberg carving long before a direct melt could occur, although direct melt and carving occur in tandem. With feedback factors including the lost heat reflectance of the retreating ice, melt at the fringes of the ice caps and sub-ice shelf melting in Antarctica could continue to significantly increase. Climate changes during the 20th century were estimated from modeling studies to have led to contributions of between 0.2 and 0.0 mm per year from Antarctica and 0.0 to 0.1 mm per year from Greenland. Estimates suggest that Greenland and Antarctica have contributed 0.0 to 0.5 mm per year over the 20th century as a result of long-term adjustment to the end of the last ice age. The current rise in sea level observed from tide gauges, of about 1.8 mm per year, is within the estimate range from the combination of factors above, but active research continues in this field. In 1992, satellites began recording the change in sea level. They display an acceleration in the rate of sea level change, but they have not been operating for long enough to work out whether this signals a permanent rate change, or an artifact of short-term variation. Short-term variability and long-term trends, on the timescale of years and decades, sea level records contain a considerable amount of variability. For example, approximately a 10 rise and fall of global mean sea level accompanied the 1997 to 1998 El Niño +or- Southern Oscillation event, and a temporary 5 fall accompanied the 2010 to 2011 event. Interannual or longer variability is a major reason why no long-term acceleration of sea level has been identified using 20th century data alone. However, a range of evidence clearly shows that the rate of sea level rise increased between the mid-19th and mid-20th centuries. Sea level acceleration up to the present has been about 0.01 m² and appears to have started at the end of the 18th century. Sea level rose by 6 cm during the 19th century and 19 cm in the 20th century. Evidence for this includes geological observations, the longest instrumental records in the observed rate of 20th century sea level rise. For example, geological observations indicate that during the last 2,000 years, sea level change was small, with an average rate of only 0.0 to 0.2 m per year. This compares to an average rate of 1.7 a ±0.5 m per year for the 20th century. Past changes in sea level. The sedimentary record. Sedimentary deposits follow cyclic patterns. Prevailing theories hold that this cyclicity primarily represents the response of depositional processes to the rise and fall of sea level. The rock record indicates that in earlier eras, sea level was both much lower than today and much higher than today. Such anomalies often appear worldwide. For instance, during the depths of the last ice age 18,000 years ago, when hundreds of thousands of cubic miles of ice were stacked up on the continents as glaciers, sea level was 120 meters lower. Locations that today support coral reefs were left high and dry, and coastlines were miles farther outward. During this time of very low sea level, there was a dry land connection between Asia and Alaska, over which humans are believed to have migrated to North America. For the past 6,000 years, the world's sea level gradually approached the current level except during marine transgressions like the older Perron. During the previous interglacial about 120,000 years ago, sea level was for a short time about 6 meters higher than today, as evidenced by wave-cut notches along cliffs in the Bahamas. There are also Pleistocene coral reefs left stranded about 3 meters above today's sea level along the southwestern coastline of West Caicos Island in the West Indies. These once submerged reefs and nearby paleo beach deposits indicate that sea level spent enough time at that higher level to allow reefs to grow. Similar evidence of geologically recent sea level positions is abundant around the world. Estimates of past changes, see Figure 11.4 in the third assessment report for a graph of sea level changes over the past 140,000 years. Sea level rise estimates from satellite altimetry since 1993 are in the range of 2.9 3.4 mm per year. Church and White report an acceleration of SLR since 1870. This is a revision since 2001, when the TAR stated that measurements have detected no significant acceleration in the recent rate of sea level rise. Based on tide gauge data, the rate of global average sea level rise during the 20th century lies in the range 0.8 to 3.3 mm per year, with an average rate of 1.8 mm per year. Recent studies of Roman wells in Caesarea and of Roman piscinae in Italy indicate that sea levels stayed fairly constant from a few hundred years AD to a few hundred years ago. Based on geological data, global average sea level may have risen at an average rate of about 0.5 mm per year over the last 6,000 years and at an average rate of 0.1 0.2 mm per year over the last 3,000 years. Since the last glacial maximum about 20,000 years ago, sea level has risen by more than 120 m as a result of melting of major ice sheets. A rapid rise took place between 15,000 and 6,000 years ago at an average rate of 10 mm per year, which accounted for 90 m of the rise. Thus in the period since 20,000 years BP the average rate was 3 mm per year. A significant event was Meltwater Pulse 1a, when sea level rose approximately 20 m over a 500-year period about 14,200 years ago. This is a rate of about 40 mm per year. The primary source may have been meltwater from the Antarctic ice sheet, perhaps causing the south to north cold pulse marked by the southern hemisphere Haremo-Muscadi cold reversal, which preceded the northern hemisphere younger dryas. Other recent studies suggest a northern hemisphere source for the meltwater in the Laurentide ice sheet. Relative sea level rise at specific locations is often 1 to 2 mm per year greater or less than the global average. Along the U.S. mid-Atlantic and Gulf coasts, for example, sea level is rising approximately 3 mm per year, U.S. tide gauge measurements. Tide gauges in the United States reveal considerable variation because some land areas are rising and some are sinking. For example, over the past 100 years, the rate of sea level rise varied from about an increase of 0.36 inches per year along the Louisiana coast, to a drop of a few inches per decade in parts of Alaska. The rate of sea level rise increased during the 1993–2003 period compared with the longer-term average, although it is unclear whether the faster rate reflected a short-term variation or an increase in the long-term trend. One study showed no acceleration in sea level rise in U.S. tide gauge records during the 20th century. However, another study found that the rate of rise for the U.S. Atlantic coast during the 20th century was far higher than during the previous 2,000 years. Amsterdam's sea level measurements, The longest-running sea level measurements are recorded at Amsterdam, in the Netherlands, part of which lies beneath sea level, beginning in 1700. Since 1850, the rise averaged 1.5 on year. Australian sea level change. In Australia, data collected by the Commonwealth Scientific and Industrial Research Organisation show the current global mean sea level trend to be 3.2 mm per year, a doubling of the rate of the total increase of about 210 mm that was measured from 1880 to 2009, which reflected an average annual rise over the entire 129-year period of about 1.6 on year. Australian record collection has a long time horizon, including measurements by an amateur meteorologist beginning in 1837 and measurements taken from a sea level benchmark struck on a small cliff on the Isle of the Dead near the Port Arthur convict settlement on July 1, 1841. These records, when compared with data recorded by modern tide gauges, reinforce the recent comparisons of the historic sea level rise of about 1.6 on year, with the sharp acceleration in recent decades. Continuing extensive sea level data collection by Australia's is summarised in its finding of mean sea level trend to be 3.2 mm per year. As of 2003, the National Tidal Centre of the Bureau of Meteorology managed 32 tide gauges covering the entire Australian coastline, with some measurements available starting in 1880. Future sea level rise. Projections, 21st century. The 2007 Fourth Assessment Report projected century-end sea levels using the Special Report on Emissions Scenarios. SRES developed emissions scenarios to project climate change impacts. The projections based on these scenarios are not predictions, but reflect plausible estimates of future social and economic development. The 6 SRES marker scenarios projected sea level to rise by 18 to 59 centimeters. Their projections were for the time period 2090-99, with the increase in level relative to average sea level over the 1980-99 period. This estimate did not include all of the possible contributions of ice sheets. More recent research from 2008 observed rapid declines in ice mass balance from both Greenland and Antarctica, and concluded that sea level rise by 2100 is likely to be at least twice as large as that presented by IPCC-AR4, with an upper limit of about 2 meters. A literature assessment published in 2010 by the U.S. National Research Council described the above IPCC projections as conservative, and summarized the results of more recent studies. These projections ranged from 56 to 200 centimeters, based on the same period as IPCC4. In 2011, Rignot and others projected a rise of 32 centimeters by 2050. Their projection included increased contributions from the Antarctic and Greenland ice sheets. Use of two completely different approaches reinforced the Rignot projection. Most recently, the Third National Climate Assessment, released May 6, 2014, projected a sea level rise of 1 to 4 feet by 2100. Decision-makers who are particularly susceptible to risk may wish to use a wider range of scenarios from 8 inches to 6.6 feet by 2100. After 2100, there is a widespread consensus that substantial long-term sea level rise will continue for centuries to come. IPCC4 estimated that at least a partial deglaciation of the Greenland ice sheet, and possibly the West Antarctic ice sheet, would occur given a global average temperature increase of 1°4 degrees Celsius. This estimate was given about a 50% chance of being correct. The estimated timescale was centuries to millennia, and would contribute 4 to 6 meters or more to sea levels over this period. There is the possibility of a rapid change in glaciers, ice sheets, and hence sea level. Predictions of such a change are highly uncertain due to a lack of scientific understanding. Modeling of the processes associated with a rapid ice sheet and glacier change could potentially increase future projections of sea level rise. Projected impacts. Future sea level rise could lead to potentially catastrophic difficulties for shore-based communities in the next centuries. For example, many major cities such as London, New Orleans, and New York already need storm surge defenses, and would need more if the sea level rose, though they also face issues such as subsidence. sea level rise could also displace many shore-based populations. For example, it is estimated that a sea level rise of just 200 could create 740,000 homeless people in Nigeria. Maldives, Tuvalu, and other low-lying countries are among the areas that are at the highest level of risk. The Union's environmental panel has warned that, at current rates, sea level would be high enough to make the Maldives uninhabitable by 2100. Future sea level rise, like the recent rise, is not expected to be globally uniform. Some regions show a sea level rise substantially more than the global average, and others a sea level fall. However, models disagree as to the likely pattern of sea level change. In September 2008, the Delta Commission, presided by Dutch politician Cees Veerman, advised in a report that the Netherlands would need a massive new building program to strengthen the country's water defences against the anticipated effects of global warming for the next 190 years. This commission was created in September 2007, after the damage caused by Hurricane Katrina prompted reflection and preparations. Those included drawing up worst-case plans for evacuations. The plan included more than $100 billion in new spending through the year 2100 to take measures, such as broadening coastal dunes and strengthening sea and river dikes. The Commission said the country must plan for a rise in the North Sea up to 1.3 meters by 2100, rather than the previously projected 0.80 meters, and plan for a 2.4 meter rise by 2200. IPCC Third Assessment. The results from the IPCC Third Assessment Report Sea Level Chapter are given below. The sum of these components indicates a rate of eustatic sea level rise from 1910 to 1990 ranging from a 0.8 to 2.2 mm per year, with a central value of 0.7 mm per year. The upper bound is close to the observational upper bound, but the central value is less than the observational lower bound, that is, the sum of components is biased low compared to the observational estimates. The sum of components indicates an acceleration of only 0.2/century, with a range from a 1.1 to plus 0.7/century, consistent with observational finding of no acceleration in sea level rise during the 20th century. The estimated rate of sea level rise from anthropogenic climate change from 1910 to 1990 ranges from 0.3 to 0.8 mm per year. It is very likely that 20th century warming has contributed significantly to the observed sea level rise, through the thermal expansion of seawater and the widespread loss of land ice. A common perception is that the rate of sea level rise should have accelerated during the latter half of the 20th century, but tide gauge data for the 20th century show no significant acceleration. Estimates obtained are based on atmosphere-ocean general circulation models for the terms directly related to anthropogenic climate change in the 20th century, that is, thermal expansion, ice sheets, glaciers and ice caps. The total computed rise indicates an acceleration of only 0.2/century, with a range from a 1.1 to plus 0.7/century. Consistent with observational finding of no acceleration in sea level rise during the 20th century. The sum of terms not related to recent climate change is a 1.1 to plus 0.9 mm per year. This range is less than the observational lower bound of sea level rise. Hence it is very likely that these terms alone are an insufficient explanation, implying that 20th century climate change has made a contribution to 20th century sea level rise. Recent figures of human, terrestrial impoundment came too late for the third report, and would revise levels upward for much of the 20th century. Uncertainty in TAR sea level projections. The different SRES emissions scenarios used for the TAR sea level projections were not assigned probabilities, and no scenario is assumed by the IPCC to be more probable than another. For the first part of the 21st century, the variation between the different SRES scenarios is relatively small. The range spanned by the SRES scenarios by 2040 is only 0.02 m or less. By 2100, this range increases to 0.18 m. Of the 6 illustrative SRES scenarios, A1FI gives the largest sea level rise and B1 the smallest. For the TAR sea level projections, uncertainty in the climate sensitivity and heat uptake of the oceans, as represented by the spread of models, is more important than the uncertainty from the choice of emissions scenario. This differs from the TAR's projections of global warming, where the uncertainty in emissions scenario and climate sensitivity are comparable in size. Minority uncertainties and criticisms regarding IPCC results, tide records with a rate of 180 century going back to the 19th century show no measurable acceleration throughout the late 19th and first half of the 20th century. The IPCC attributes about 60 century to melting and other eustatic processes, leaving a residual of 120 of 20th century rise to be accounted for. Global ocean temperatures by Levitas al. Are in accord with coupled ocean-atmosphere modeling of greenhouse warming, with heat-related change of 30 Melting of polar ice sheets at the upper limit of the IPCC estimates could close the gap, but severe limits are imposed by the observed perturbations in Earth rotation. By the time of the IPCC TAR, attribution of sea level changes had a large unexplained gap between direct and indirect estimates of global sea level rise. Most direct estimates from tide gauges give 1.5 euro 2.0 mm per year, whereas indirect estimates based on the two processes responsible for global sea level rise, namely mass and volume change, are significantly below this range. Estimates of the volume increase due to ocean warming give a rate of about 0.5 mm per year, and the rate due to mass increase, primarily from the melting of continental ice, is thought to be even smaller. One study confirmed tide gauge data is correct, and concluded there must be a continental source of 1.4 mm per year of fresh water. In the last dozen years, published values of 20th century GSL rise have ranged from 1.0 to 2.4 mm per year. In its third assessment report, the IPCC discusses this lack of consensus at length and is careful not to present a best estimate of 20th century GSL rise. By design, the panel presents a snapshot of published analysis over the previous decade or so and interprets the broad range of estimates as reflecting the uncertainty of our knowledge of GSL rise. We disagree with the IPCC interpretation. In our view, values much below 2 mm per year are inconsistent with regional observations of sea level rise and with the continuing physical response of Earth to the most recent episode of deglaciation. The strong 1997–1998 El Niño ±0 caused regional and global sea level variations, including a temporary global increase of perhaps 20 The IPCC TAR's examination of satellite trends says, the major 1997–98 El Niño ±0 southern oscillation event could bias the above estimates of sea level rise and also indicate the difficulty of separating long-term trends from climatic variability. Glacier contribution. It is well known that glaciers are subject to surges in their rate of movement with consequent melting when they reach lower altitudes and/or the sea. The contributors to Annals of Glaciology, 3, Volume 36 discuss this phenomenon extensively, and it appears that slow advance and rapid retreat have persisted throughout the mid to late Holocene in nearly all of Alaska's glaciers. Historical reports of surge occurrences in Iceland's glaciers go back several centuries. Thus rapid retreat can have several other causes than CO2 increase in the atmosphere. The results from Deirdre show a sharp increase in the contribution of mountain and subpolar glaciers to sea level rise since 1996 to 1998, with an average of about 0.35 mm per year since 1960. Of interest also is Arendt et al., who estimate the contribution of Alaskan glaciers of 0.14 ± 0.04 mm per year between the mid-1950s to the mid-1990s, increasing to 0.27 mm per year in the middle and late 1990s. Greenland contribution, Krabel et al. Estimate a net contribution from Greenland to be at least 0.13 mm per year in the 1990s. Juffin et al. Have measured a doubling of the speed of Jarkshave-Nisbra between 1997 and 2003. This is Greenland's largest outlet glacier. It drains 6.5% of the ice sheet, and is thought to be responsible for increasing the rate of sea level rise by about 0.06 millimeters per year, or roughly 4% of the 20th century rate of sea level increase. In 2004, NOAA estimated a contribution of 0.04 plus or minus 0.01 millimeter per year to sea level rise from southeast Greenland. NOAA and Kanagaratnam produced a comprehensive study and map of the outlet glaciers and basins of Greenland. They found widespread glacial acceleration below 66 n in 1996 which spread to 70 n by 2005. And that the ice sheet loss rate in that decade increased from 90 to 200 cubic kilometers per year. This corresponds to an extra 0.25 0.55 millimeter per year of sea level rise. In July 2005 it was reported that the Kangerlussuaq Glacier, on Greenland's east coast, was moving towards the sea 3 times faster than a decade earlier. Kangerlussuaq is around 1,000 m thick, 7.2 km wide, and drains about 4% of the ice from the Greenland ice sheet. Measurements of Kangerlussuaq in 1988 and 1996 showed it moving at between 5 and 6 km per year, while in 2005 that speed had increased to 14 km per year. According to the 2004 Arctic Climate Impact Assessment, climate models project that local warming in Greenland will exceed 3 degrees Celsius during this century. Also, ice sheet models project that such a warming would initiate the long-term melting of the ice sheet, leading to a complete melting of the Greenland ice sheet over several millennia, resulting in a global sea level rise of about 7 meters. Antarctic contribution. On the Antarctic continent itself, the large volume of ice present stores around 70% of the world's fresh water. This ice sheet is constantly gaining ice from snowfall and losing ice through outflow to the sea. West Antarctica is currently experiencing a net outflow of glacial ice, which will increase global sea level over time. A review of the scientific studies looking at data from 1992 to 2006 suggested a net loss of around 50 gigatons of ice per year was a reasonable estimate, although significant acceleration of outflow glaciers in the Amundsen Sea embayment could have more than doubled this figure for the year 2006. East Antarctica is a cold region with a ground base above sea level and occupies most of the continent. This area is dominated by small accumulations of snowfall which becomes ice and thus eventually seaward glacial flows. The mass balance of the East Antarctic ice sheet as a whole is thought to be slightly positive or near to balance. However, increased ice outflow has been suggested in some regions. In 2011 ice-penetrating radar led to the creation of the first high-resolution topographic map of one of the last uncharted regions of Earth, the Aurora subglacial basin, an immense ice-buried lowland in East Antarctica larger than Texas. The map reveals some of the largest fjords or ice-cut channels on Earth. Because the basin lies kilometers below sea level, seawater could penetrate beneath the ice, causing portions of the ice sheet to collapse and float off to sea. The map is expected to improve models of ice sheet dynamics. Shepard al. 2012, found that different satellite methods were in good agreement and combing methods leads to more certainty with East Antarctica, West Antarctica, and the Antarctic Peninsula changing in mass by +14 a ±43, a Euro65 a ±26, and a Euro20 a ±14 gigatons per year. Effects of snowline and permafrost. The snowline altitude is the altitude of the lowest elevation interval in which minimum annual snow cover exceeds 50%. This ranges from about 5,500 meters above sea level at the equator down to sea level at about 65 degree N and S latitude, depending on regional temperature amelioration effects. Permafrost then appears at sea level and extends deeper below sea level polewards. The depth of permafrost and the height of the ice fields in both Greenland and Antarctica means that they are largely invulnerable to rapid melting. Greenland summit is at 3,200 meters, where the average annual temperature is -32 degrees Celsius. So even a projected 4 degrees Celsius rise in temperature leaves it well below the melting point of ice. Frozen Ground 28, December 2004, has a very significant map of permafrost-affected areas in the Arctic. The continuous permafrost zone includes all of Greenland, the north of Labrador, NW territories, Alaska north of Fairbanks, and most of NE Siberia north of Mongolia and Kamchatka. Continental ice above permafrost is very unlikely to melt quickly. As most of the Greenland and Antarctic ice sheets lie above the snowline and/or base of the permafrost zone, they cannot melt in a time frame much less than several millennia. Therefore they are unlikely to contribute significantly to sea level rise in the coming century. Polar ice: the sea level will rise above its current level if more polar ice melts. However, compared to the heights of the ice ages, today there are very few continental ice sheets remaining to be melted. It is estimated that Antarctica, if fully melted, would contribute more than 60 meters of sea level rise, and Greenland would contribute more than 7 meters. Small glaciers and ice caps on the margins of Greenland and the Antarctic peninsula might contribute about 0.5 meters. While the latter figure is much smaller than for Antarctica or Greenland, it could occur relatively quickly, whereas melting of Greenland would be slow and Antarctica even slower. However, this calculation does not account for the possibility that as meltwater flows under and lubricates the larger ice sheets, they could begin to move much more rapidly towards the sea. In 2002, Rignot and Thomas found that the West Antarctic and Greenland ice sheets were losing mass, while the East Antarctic ice sheet was probably in balance. Kwok and Camiso also discovered the temperature and pressure anomalies around West Antarctica and on the other side of the Antarctic peninsula correlate with recent southern oscillation events. In 2004, Rignot al. estimated a contribution of 0.04 a plus or minus 0.01 a mm per year to sea level rise from southeast Greenland. In the same year, Thomas al. found evidence of an accelerated contribution to sea level rise from West Antarctica. The data showed that the Amundsen Sea sector of the West Antarctic ice sheet was discharging 250 cubic kilometers of ice every year, which was 60% more than precipitation accumulation in the catchment areas. This alone was sufficient to raise sea level at 0.24 a mm per year. Further, thinning rates for the glaciers studied in 2002 a Euro 03 had increased over the values measured in the early 1990s. The bedrock underlying the glaciers was found to be hundreds of meters deeper than previously known, indicating exit routes for ice from further inland in the Byrd subpolar basin. Thus the West Antarctic ice sheet may not be as stable as has been supposed. In 2005 it was reported that during 1992 a Euro 2003, East Antarctica thickened at an average rate of about 18 a mm per year, while West Antarctica showed an overall thinning of 9 a mm per year associated with increased precipitation. A gain of this magnitude is enough to slow sea level rise by 0.12 a plus or minus 0.02 a mm per year. Effects of sea level rise: based on the projected increases stated above, the IPCC TAR-WGII report notes that current and future climate change would be expected to have a number of impacts, particularly on coastal systems. Such impacts may include increased coastal erosion, higher storm surge flooding, inhibition of primary production processes, more extensive coastal inundation, changes in surface water quality and groundwater characteristics, increased loss of property and coastal habitats, increased flood risk and potential loss of life, loss of non-monetary cultural resources and values, impacts on agriculture and aquaculture through decline in soil and water quality, and loss of tourism, recreation, and transportation functions. There is an implication that many of these impacts will be detrimental especially for the 3/4 of the world's poor who depend on agriculture systems. The report does, however, note that owing to the great diversity of coastal environments, regional and local differences in projected relative sea level and climate changes, and differences in the resilience and adaptive capacity of ecosystems, sectors, and countries, the impacts will be highly variable in time and space. Statistical data on the human impact of sea level rise is scarce. A study in the April 2007 issue of Environment and Urbanization reports that 634 million people live in coastal areas within 30 feet of sea level. The study also reported that about two-thirds of the world's cities with over 5 million people are located in these low-lying coastal areas. The IPCC report of 2007 estimated that accelerated melting of the Himalayan ice caps and the resulting rise in sea levels would likely increase the severity of flooding in the short term during the rainy season and greatly magnify the impact of tidal storm surges during the cyclone season. A sea level rise of just 400 mm in the Bay of Bengal would put 11% of the Bangladesh's coastal land underwater, creating €10 million climate refugees. Island nations. IPCC assessments suggest that deltas and small island states are particularly vulnerable to sea level rise caused by both thermal expansion and ocean volume. Sea level changes have not yet been conclusively proven to have directly resulted in environmental, humanitarian, or economic losses to small island states, but the IPCC and other bodies have found this a serious risk scenario in coming decades. Many media reports have focused on the island nations of the Pacific, notably the Polynesian islands of Tuvalu, which based on more severe flooding events in recent years, were thought to be sinking due to sea level rise. A scientific review in 2000 reported that based on University of Hawaii gauge data, Tuvalu had experienced a negligible increase in sea level of 0.07 a year over the past 2 decades, and that ENSO had been a larger factor in Tuvalu's higher tides in recent years. A subsequent study by John Hunter from the University of Tasmania, however, adjusted for ENSO effects and the movement of the gauge. Hunter concluded that Tuvalu had been experiencing sea level rise of about 1.2 mm per year. The recent more frequent flooding in Tuvalu may also be due to an erosional loss of land during and following the actions of 1997 cyclones Gavin, Heine, and Kelly. Besides the issues that flooding brings for these island states, the island states themselves would also become dissolved over time, as the islands becomes uninhabitable or becomes completely submerged by the sea. Once this happens, all rights on the surrounding area are removed. This area can be huge as rights extend to a radius of 224 nautical miles around the entire island state. Any resources within this area can be freely dug up by anyone and sold without needing to pay any commission to the island state. Numerous options have been proposed that would assist island nations to adapt to rising sea level. Cities. Miami has been listed as the #1 most vulnerable city worldwide in terms of potential damage to property from storm-related flooding and sea level rise. Satellite sea level measurement. Current rates of sea level rise from satellite altimetry have been estimated in the range of 2.9 a €3.4 a plus or minus 0.4 a €0.6 mm per year for 1993 a €2010. This exceeds those from tide gauges. It is unclear whether this represents an increase over the last decades. Variability. True differences between satellites and tide gauges. Or problems with satellite calibration. Knowing the current altitude of a satellite which can measure sea level to a precision of about 20 mm is primarily complicated by orbital decay and the difference between the assumed orbit and the Earth geoid. This problem is partially corrected by regular recalibration of satellite altimeters from land stations whose height from MSL is known by surveying. Over water, the height is calibrated from tide gauge data which is needed to correct for tides and atmospheric effects on sea level. Individual studies. Aplane et al. Looked at trends in mean sea level. A global MSL curve was plotted using data for the 1993–2008 period. Their estimates for mean rate of sea level rise over this time period was 3.11 mm per year. A correction was applied to this resulting in a higher estimate of 3.4 mm per year. Over the 2005 to 2008 time period, the MSL rate was estimated to be 1.09 mm per year. This is a reduction of 60% on the rate observed between 1993 and 2005. MSL was also plotted using data between the years 1994 and 2007. Their data for this time period show 2 peaks in MSL rates for the years 1997 and 2002. These maxima very likely reflected the influence of the ENSO on MSL. Using the 1994–2007 MSL data, They estimated MSL rates using moving windows of 3 and 5 years. Lower rates were observed during La Niña plus or minus events in 1999 and 2007. They concluded that the recently observed reduction in the MSL rate was likely to be real, since it coincided with an exceptionally strong La Niña plus or minus event. Preliminary analyses suggested that an acceleration of the MSL trend would likely occur in relationship with the end of the 2007 08 La Niña plus or minus event. White reported measurements of near global sea level made using satellite altimeters. Over the time period January 1993 to April 2011, these data show a steady increase in global mean sea level of around 3.2 mm per year, with a range of plus or minus 0.4 mm per year. This is 50% larger than the average rate observed over the 20th century. White was, however, unsure of whether or not this represented a long-term increase in the rate. The Centre National d'études spatiales collect localization satellites reported on the estimated increase in GMSL between 1993 and 2011. Their estimate was an increase of 3.22 mm per year, with an error range in this trend of approximately 0.6 mm per year. The CU Sea Level Research Group estimated the rate of GMSL between 1993 and 2011. The rate was estimated at 3.2 mm per year, with a range of plus or minus 0.4 mm per year. The Laboratory for Satellite Altimetry estimated the trend in GMSL over the time period 1992 to 2011. Their estimate was a trend of 2.9 mm per year, with a range of plus or minus 0.4 mm per year. According to the LSA, the estimates of sea level rise do not include glacial isostatic adjustment effects on the GOID, which are modeled to be plus 0.2 to plus 0.5 mm year when globally averaged. See also 8.2 Kiloyear event, Antarctic cold reversal, carbon cycle, coastal development, coastal sediment supply, drawdown, effects of global warming on oceans, fossil water, hydrosphere, islands first, lists of environmental topics, list of global climate system components, Aldebaran transgression, overdrafting, retreat of glaciers since 1850, standard sea level, transgression, water cycle, long period tide. Notes. References, IPCCR 4WG1, Solomon, S. Quin, D. Manning, M. Chen, Z. Marquis, M. Averett, K.B. Tigner, M. and Miller, H.L., ed., Climate Change 2007, A Physical Science Basis, Contribution of Working Group I to the Fourth Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press, ISBN A978-0-521-88009-1A. IPCCR 4WG2, Parry, M.L. Kantsiani, O.F. Palitnikov, J.P. Van der Linden, P.J. and Hansen, C.E., ed., Climate Change 2007, Impacts, Adaptation and Vulnerability, Contribution of Working Group 2 to the Fourth Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press, ISBN A978-0-521-88010-7A. IPCCR 4WG3, Metz, B. Davidson, O.R. Bosch, P.R. Dave, R. and Mayer, L.A., ed., Climate Change 2007, Mitigation of Climate Change, Contribution of Working Group 3 to the Fourth Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press, ISBN A978-0-521-88011-4A. IPCCR Fawcett, Call Writing Team. Pachauri, R.K. and Raisinger, A., ed., Climate Change 2007, Synthesis Report, Contribution of Working Groups I, 2 and 3 to the Fourth Assessment Report of the Intergovernmental Panel on Climate Change, IPCC, ISBN A92-9169-122-4A. IPCC TAR WG1, Horton, J.T. Ding, Y. Griggs, D.J. Noga, M. Van der Linden, P.J. Dye, X. Maskell, K. and Johnson, C.A., ed., Climate Change 2001, The Scientific Basis, Contribution of Working Group I to the Third Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press, ISBN A0-521-80767-0A. IPCC TAR WG2, McCarthy, J.J. Canziani, O.F. Leary, N.A. Doken, D.J. and White, K.S., ed., Climate Change 2001, Impacts, Adaptation and Vulnerability, Contribution of Working Group 2 to the Third Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press, ISBN A0-521-80768-9A. IPCC TAR WG3, Metz, B. Davidson, O. Swart, R. and Pan, J., ed., Climate Change 2001, Mitigation, Contribution of Working Group 3 to the Third Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press, ISBN A0-521-80769-7A. Further reading. External links, Third National Climate Assessment Sea Level Rise Key Message, University of Colorado at Boulder Sea Level Changer, Technical Considerations for Use of Geospatial Data in Sea Level Change Mapping and Assessment NOAA Technical Report NOS 2010-01, Incorporating Sea Level Change Scenarios at the Local Level outlines 8 steps a community can take to develop site-appropriate scenarios. East Coast faces faster sea level rise. Cities from North Carolina to Massachusetts sea waters rising more rapidly. July 28, 2012. Volume 182 Number 2 Science News, Climate Change Threatening the Southern Ocean. CSIROA, Sea Level Rise, Understanding the Past Improving Projections for the Future, Providing New Homes for Climate Exiles. Sujatha Biravan and Satyachala Rajan, 2006. Sea Level Rise Cluster of Excellence Future Ocean, University of Kiel, New Perspectives for the Future of the Maldives. Nils Axel Mar Paragraph RNER, Michael Tooley, Gar Paragraph Ramposh Nert, 2004, Physical Agents of Land Loss, Relative Sea Level. An Overview of Coastal Land Loss, with emphasis on the southeastern United States. U.S. Geological Survey. Retrieved February 14, 2005. Changes in the Earth's shorelines during the past 20 ki caused by deglaciation of the late Pleistocene ice sheets, from the Permanent Service for Mean Sea Level, Indigenous Aboriginal Australian Perspective on Sea Level Changes, video, includes picture of sea level for past 20 ki based on Barbados Coral Record, Sea Level Rise FAQ, the Global Sea Level Observing System, the GLOS Station Handbook, Sea Level Rise Reports. United States Environmental Protection Agency. Archived from the original on April 20, 2009. The Sinking of Tuvalu, Sea Level Rise Center for the Remote Sensing of Ice Sheets. University of Kansas. Maps, animations, GIS layers, tides and sea level rise model, maps that show a rise in sea levels, sea level rise and coastal flooding impacts. Viewer displays potential future sea levels, provides simulations of sea level rise at local landmarks, communicates the spatial uncertainty of mapped sea levels, models potential marsh migration due to sea level rise, overlays social and economic data onto potential sea level rise, and examines how tidal flooding will become more frequent with sea level rise. NOAA Coastal Services Center. Sea level rise of up to 14 ma. Meltdown of Greenlandic ice shield, world maps for a sea level rise and 60 ma. Meltdown of the Antarctic ice shield, hazard map showing variable sea level rise and earthquake impacts, developed by SeaArc to demonstrate potential impact of climate change on World Heritage Sites. Sea Levels Online, National Ocean Service, displays local sea level rise and sea level trends via a map interface. Sea level rise planning maps, county and state scale map showing which lands below 5 meters are likely and unlikely to be protected from a rising sea, according to study funded by the United States Environmental Protection Agency. Sea level rise: how much and how fast will sea level rise over the coming centuries? Past. Sea level rise: how much and how fast will sea level rise over the coming centuries? Present. National Geographic Photo Gallery, Sea Level Rise.